Okay, let's continue. Our next speaker is Denys Romash. He will present a talk titled On Lower Distance, Estimates for One Class of Homomorphism. Please welcome.
So today I will provide a short presentation on our recent work on lower distance estimates for one class of homomorphism, prepared by Natalia Ilkevich, myself, Denys Romash, and Yevgen Sevastyanov, and Dr. Yevgen Sevastyanov, sorry, and we are all representing Zhytomyr Ivan Franko State University. So, one moment. Yeah. So what was our motivation of this work? That in many applications, for example, in fluid flow or image processing, we need to know how much mapping can compress or distort small distances. And for classical quasi-conformal mappings in Euclidean spaces, we have explicit exponential lower bounds that prevents point from collapsing too closely. And our goal is to show that the similar bounds can be achieved using only Lebesgue's norm of distortion function Q. And these bounds hold in every general metric spaces, not just in Euclidean spaces. And those lower bounds are not dependent on the exact form of the function. So some key definitions already was explained what is a Q-ring Q homomorphism. And one remark that intuitively that like we have two spheres, two poles, yeah, and some rubber bands that are stretched between these concentric spheres, and the modulus captures their thickness. So the Poletsky inequality also prevents any such family from being pitching too thin. So this is like intuitive illustration of how the ring Q homomorphism works. The next definition which were used in our proof is the definition of of QED domain, that is a quasi-extremal distance domain, which means that every Euclidean domain D belongs to Rn, called quasi-extremal if there exists any constant A that is more or equal than 1, and that such for any two disjoint continua inside D, we have this inequality. So what does it mean? That if we have some domain, yeah, the modulus inside this domain will be more than outside this domain, and this more in measurable times. So this A is a constant, which is measuring the times so that our P modulus is bigger inside. So, and third definition is the n-loner space. Is a metric measured space where the loner function stays positive for all t that are more than 0. So nt should be rather small. So this prevents our bottlenecks at the scale t, and we understand that every pair of continua within relative distance t forces a uniform positive modulus. So shortly about the results that we got in our work. So let D belongs to Rn, so it exists in Rn. Q belong to the L1 function on D, and key is inside D is a compact. So distance between K and boundary of D is bigger than 0. Our function should belong to the class first of all QED. Second of all, it will be measurable and bounded by the Q, and should be a ring Q homomorphism on the compact T inside D. So total distortion Q controls our shrinking, and a lower distance does not depend on the function. So our main result is that the difference between model of the distance between the f from x and f from y more or equal this exponential form. So it depends only on constants, which are bigger than 0, and on the measure of the space. And the same result we were get inside the more general metric spaces. So if again this function between metric spaces, our x prime is in Lorentz space, and our q belongs to L1 and measures total distortion. So under all this assumption, for all x, y belongs to k, there are also existed constants c and c1 that are bigger than 0, that our this equation is true. So our key ideas of this proof was to use the upper bound using the ring homomorphism inequality to estimate p modulus of family of cures. Second step was to understand our lower bound, applying quasi-extremal distance and lower condition to bound original models from below by an exponential term, and combine these two theories. We are matching these bounds to derive the explicit distance ring estimate. Why it would be important? First of all, we can show that the uniform limits preserve these properties. So hypothesis that a sequence of approximating mappings are converging uniformly to F on D remains open and discrete. One use case we were found that in mesh-based elastic simulation, refining the grid won't introduce self-intersection of faults. So it could be used in dynamic modeling of 3D animation. So on the other hand, the boundary behavior exponential estimates control cluster sets at boundary points. Use case is, for example, in a medical imaging elastography, where constructed tissues maps remain stable near organ boundaries, avoiding artificial singularities. And third potential application is economic forecasting and time series mappings. So when one model of evolution of macroeconomic indicators as a map between state spaces explicit lower distance bound guarantees that distinct economic regimes, so like a growth or recession, stay distinguishable under forecast transformations. So during the stress testing and scenario analysis, these bounds prevent our prediction models from collapsing extreme downturns into average outputs, improving the robustness of our for economic forecasts. So the main conclusion that our work derived explicit potential lower bounds for distance distortion in Euclidean and metric settings, and generalized classical quasi-conformal lower bound techniques, broader context. If you are interested in the full proof path, you can find it on the archive already, and also in the magazine on lower distance estimates of mapping in metric space. This our article inside the Rediconti del Circolo Matematico di Palermo. It is now in print. So as from now, that's all. If you have any question, do not hesitate to ask.
Thanks, Denys.